Okay guys, I hope this is a better way to explain the heating curve problem. Alright, so we have a graph with the temperature on the vertical axis and the heat on the horizontal axis. And for any state that we're doing a heating curve for, we're assuming it's at one pressure. So it's going to go from solid to liquid to gas. We don't have to mess with supercritical fluids or anything like that. But when we're going from solid to liquid, we have a phase change intermediate, and from liquid to gas, we also have a phase change that's intermediate. And I've labeled these heats Q1 for when it's transforming within the solid phase, Q2 for when it's transforming for the phase change, and Q3 when the temperature is changing within the liquid phase, Q4 for when the phase change is going on between liquid and gas, and Q5 for when the temperature is changing within the gas phase. Alright, so some things that we learned last semester is that we learned the Q equals M, which is the mass or number of grams of the substance. You also could be given moles, and you may have to convert that, and a C, which is the specific heat capacity of the substance for the particular phase that it's in. So this C will vary from the solid to the liquid to the gas phase. And the delta T, this is the final temperature minus the initial temperature within that phase. Because phase changes do not involve temperature changes themselves, and the temperature is constant, which we can tell by the flat line, or reasonably flat because my drawing kind of sucks. We will not be using this formula for the phase changes, but it costs us energy and heat to go from a solid all the way up to a gas, or we're releasing energy all the way from the gas down to the solid if we were to reverse the process. So in order to do a problem like this, what we need to do is, if we were, say, starting from a -5 degrees Celsius to a 105 degrees Celsius for something like water, what we would do is, in the solid phase, Q1 would equal the number of grams of water, which let's say we have 18, times the heat capacity for water in its liquid phase. And you guys will be given this in Mastering Chemistry, or can look it up in your book. And that's times the delta T, which is the temperature final minus the temperature initial. So since we're going from -5 degrees, which is our temperature initial, it's 0 minus the -5 degrees Celsius. And that'll give us some number of joules. Okay? And then to do this phase change between the solid and the liquid, we'll be taking into account the enthalpy of fusion, which is this delta H FUS that you guys will see, and that's some number of kilojoules per mole. And you can look that up. It's if you can do this, and once you get it, you can do it for anything, not just water. This is just kind of an example. So you're going to take the number of grams, which will actually be this same number of grams from down here, times 1 over the formula weight for water. So if that's water, it's like 18.02 grams. And you guys can add that up from the periodic table if we don't give it to you on the exam. And we're multiplying that by a number of kilojoules per mole. So that'll give us some number of kilojoules. So in the end, we're going to have to convert the joules from down here into kilojoules in order to be able to add these together. So to do that, you're going to take the number of joules times 1 kilojoule over 1,000 joules to get the number of kilojoules. Okay, and you'll have to do that every time you get joules, get it into kilojoules so they can be added for each step. So then within the liquid phase, we're going to take the same number of grams that we've been using times the number of joules per gram degrees Celsius, which is a different heat capacity than the heat capacity for the solid was. You guys will be given that, or you can look it up in your book. Times the delta T, which within the liquid phase of water, our ending temperature in liquid phase is 100 degrees minus 0 degrees, because that's where the water starts being water. So that'll give us some number of joules, which you'll again have to convert to kilojoules. Then you have to take into account this phase change from liquid to gas. So for here, you can either be lazy and take the number of moles that you calculated down here if you did that as its own step, and you can plug it in times the heat, enthalpy of vaporization, which is some different number of kilojoules per mole that you will be given or can look up. Or you can go ahead and multiply the number of grams times 1 mole over the 18 grams if we're using water, times the number of kilojoules per mole that we get from the heat of vaporization. And that'll give us some number of kilojoules. And then if we were to heat the gas and we weren't just stopping at gas, we would have to take into account this phase change. And so since we said we were going to heat it to 105 degrees Celsius, you'll take the same number of grams that we've been using this whole time, plus the number of joules per gram degree Celsius, which this is the heat capacity of the steam, which will be different from the heat capacity of the liquid or the solid. And you'll multiply that by the final temperature, which I said was going to be 105 degrees, minus the 100 degrees, which is when it becomes steam. Okay, so I'm hoping that helped. And basically what we're going to do from there is, sorry, we're going to add up our total heat, which is Q1 plus Q2 plus Q3 plus Q4 plus Q5, and you're all set. So a handy trick for wondering if you're right or not, heating it up is always going to be an endothermic process. We always have to invest energy. And because our final temperature is always higher than our initial temperature when we're heating it up, our Q is always going to come out positive because our delta T is positive. And when we're cooling it down, it's always going to be exothermic, so our Q is always going to be negative because when we are heating it up, the final temperature is lower than the initial temperature, so the delta T will come out negative. So I hope that helps, and I hope this is a little more clear than my prior video with all its crazy shakiness.